have liver, we have kidneys, we have sigmoid, we have bladder, we have all of these wonderful things on top of each other. Make sense? Over here, we are now eliminating that. We are going back and saying, okay, we're going to take all of these different types of axial views and we're going to reconstruct them into these types of images. But they won't even look the same because we know that this coronal image is at a certain level, right, of where that's going to be placed and what you're going to be able to see, eliminating all of the extra abdominal organs that superimpose it. Like over here, I just mentioned we have liver sitting on top of kidneys and so on and so forth. Here we have no liver, we see the kidneys. Makes sense? So we've removed a lot of the other organs by taking it from this level and now affecting it or placing it in this reconstruct, which is going to be more right because this is just going to be like one slice up here. Does everybody understand the differences? That's the only difference. But because we're doing it slice by slice, we're going to be increasing radiation dose. So that's going to be one thing, right? Who can recall what contrast resolution is back from X-ray? Huh? The grays between, you're talking about very bright, and very dark, right? So that's the one thing about, if you're looking at these images, you can go back and say, okay, we have some very brights, and we have some very darks. That's going to be the contrast resolution of CT. If you look at this chest, two chests, let's take a look at both chests on each side. We have that long scale, and then we have the short scale, right? Do you remember what that means? Long scale, low contrast, short scale, high contrast. Is that ringing a bell? No? Never heard of it in a day of my life. Never.
No, I heard of it. It's always blacks and whites, right? Any other grays?
Very good. So it is coming back. So when we think of, and I remember correctly, we're thinking of all of these different shades of pixels, right? So if you had a long scale or bright. Now you're saying, okay, if you have a scale, you have to go from this color to here, right, to a brighter. If you have a short scale, meaning you don't have black and white, you have less distinctions between the two, right? You have to get to bright very quickly. So this one is probably going to be semi-bright. This one's probably going to be semi-dark, correct? Not a lot of transition in between. But when you're talking about over here, you have some transition. So this might be a dark between here, and then you go from here a little bit less dark, and then here is a little bit more gray, and then here you go a little bit brighter, and then here's brighter. So you have more of a transition. The longer the scale, the more differences that you have in your anatomy, okay? The shorter the scale, the less that you have. This is the amount of contrast that you're able to distinguish one from the other. So when you have a long scale, you have lower contrast differences between one to the other. But when you have high contrast, you have very distinct differences between one to the other. Now I want you to focus that, with that knowledge, I want you to focus on our chest radiograph here, and now our chest CT. Which one has a higher contrast? Why does this one have a higher contrast?
Because the difference is very, very sharp.
It looks like the colors were probably basic to limited to very, very, it's either dark or it's bright, right? Not a lot of in between. But when you see this, you see some varying shades of gray, you see a transition from here to here, then they go over here, and you start thinking, oh, well, that's gonna have the different types of coloration or differentiation between tissue, which is going to be a long scale. So when you have a long scale, you have very little contrast. Not a big difference. Contrast is the differences between one to the other. When you have a high contrast, right, there's a big difference between one to the other. Low contrast, not a lot of differences between bone and tissue. Bone, highly dense, tissue, not so dense. Okay? I know this is exciting, but that's what we're going to get into in this chapter. All right. So, unlike conventional radiography, you're looking at computed tomography, shows some cross-sectionals. We know that transaxial or axial images is the way that we're acquiring the data. Shows three-dimensionals. We're able to go back and recreate that coronal and those sagittal views and even more based on the software that we're using, created from the data set. What is a data set? Not hard. Huh? There you go. What did you say it loud and proud? That is the energy, the points of energy, the points of information that was acquired from the detector. Remember, it was an analog wave. The X-ray was received. It is now electrical. That is all data sets. Because what's going to make a difference is that if you are here, right, put our heart right there. If I am taking it from here, this is my slice of volume, then the data set that was acquired from all of these different points on that detector is going to have a different type of energy. So when it deposits that energy, once, remember, from an X-ray tube, we have the primary beam, we have the patient, and now we have the remnant beam. Here are detectors. So all of this energy is going to be referenced as to what it passed through. If the heart is right here, this is going to have lesser energy. If this is the lungs, it's going to have higher energy because it's easier to pass through. Make sense? This is air. Nothing should have attenuated it. What does attenuation mean again? Absorb or scatter. It's the loss of photons. Attenuation just basically means the loss of photons. How? Either through absorption or scatter. That's it. That's what attenuation is. So air outside of the patient, there should be no attenuation. Those photons should reach the detectors without having anything else. The photons that pass through the chest, the lungs, should have a lot more landing on the detectors, right? But when we get across the spine and the heart and all of the tissue, we're expecting to have more absorption. Make sense? So let's take a look at this image. Let's put it in. Just doesn't work. Okay. Think about the slice right here. Well, here it is, right? Here's the slice. If X-rays are coming down, and here are the detectors, we know that out here, we're not going to have any attenuation, right? This is air outside of the patient, landing on the detectors. It has a different color, yes? This color right here? Now, X-rays that are going through this tissue and landing on the detectors has a different color. Yes? The X-rays that are passing through this part of the body we can definitely go back and see that some of those photons are going to have some absorption, are going to have some transmission, and then in between. This is how we're able to see that we're looking at lungs and we're looking at a heart. How do we know that? Because of the way that the photons interacted with the body at that level. The truth. That's how we know, and that's called the data set. If we don't have that information to start with, we won't ever form an image. So, when we're thinking about radiography, again, everything is superimposed. If you're looking at the X-ray tube, and this is the quality check, moving through, you're going to have a circle, a triangle, and a box all superimposed over each other. You wouldn't be able to tell what level the box was in. You wouldn't be able to tell what level the triangle is in. You wouldn't be able to tell what level the circle is in. They would all be fully superimposed. Okay? So other limitations, again, for radiography, slight density changes. This is what we're talking about, whether you have a short scale or a long scale. In CT, we're going to continue working through what is higher contrast resolution. That's just going to be the part. And so when we get to Hounsfield units today, you'll understand why those numbers are the numbers. I know I've said a lot over here. And we're going to get into short scale. We're going to talk about contrast resolution, but is everybody okay with the limitations of radiography over computed tomography? Okay, so what is the limitation of radiography? Superimposition of body parts. Okay, what else? Our contrast resolution abilities. In computed tomography, we're going to have greater contrast resolution. Okay? Now, we're talking about conventional tomography. You remember the word tomography from the last chapter, or 2 chapters ago? What was tomography? This is how we all started. It took it in slices, but what was the difference between that? Do you remember? Like, no, it's not so long ago. Like 2 weeks ago. I'm joking. Anybody remember what conventional tomography was about? I'm gonna be crying all the way home. Goodness. As I'm eating my cake for comforting. Come on, guys. Think about it. I'll draw it for you. I know you like my drawings. I've never seen that a day in my life. It is tomography. This is how it started. This is how the concept became that you can take imaging in slices. So back in the day, when we didn't have CT, or I guess we had CT, but CT was costly, you would have an X-ray tube aligned with the image receptor. The X-ray tube would travel over to the left, aligned with, and then the image receptor would travel to the right, and it would start to take, as it traveled over to the other side, it would continue to take a continuous beam. You would hear beep all the way through. However, the X-ray tube were never misaligned with the image receptor. It always stayed centered. When we did this, kidneys were probably what we were looking for. So as it traveled, this information, we were able to take our first slicing, meaning that if we adjusted the tube, we would be able to take the kidneys and blur everything out that wasn't in the center of the machine. So we would adjust our X-ray tube to our level of where those kidneys are, and we would continue to move. That was our first slicing image. Okay. CT just came through and continued to improve it. So what had happened on the first images, you would have kidneys, but then you would have blur everywhere else. On the CT, you don't see any blur anywhere else. You see clear, right? You see what you need to see. And an old, let's take a trip to Google. Let's see if IVP comes over, because that's what I'm trying to. Old IVP, obviously all of this has been replaced with CT.
Can you compare it to Panax?
Panorax, because it's a curved, not so much. Even though the sides are really, these are scouts. I'm really trying to show you like one old, goes in there, but we still teach it. There's one in your book. I have to go back and look at it to see, but it's. Alright, let's see if I can put an IVP machine. Ah, perfect. Look at that. So what you're seeing is what is a conventional type tomograph. You see the blurring of everything around it? All that you're really able to see because of the way that we were leveling this is going to be at the kidneys. Everything else on top of superior to the kidneys and inferior to the kidneys are blurred out. You're not really seeing anything happen. You see motion, but that's intentional motion. Intentional motion to, as this is moving across, obviously the patient is not breathing, as this is moving across, causing motion, it's blurring everything else out. That is an original tomogram, tomography. But what you're looking at it, and is why is it considered CT or the birth of CT, is because you're looking without the liver. You don't see a liver there, right? You don't see a colon across. You don't see a stomach coming through. None of that is superimposed. We didn't take it out of the patient. All we had to do was just go back and blur and center. So that was the concepts of what conventional tomography started leading to what is computed tomography. And that's the reconstruction eventually of going from an axial image. And that's not an axial image. That's a plain radiograph. Does everyone see that? That's an X-ray image. It's just a specialized type of technique. And that's what the moving of the X-ray to. Causing blur. All right. I know, exciting. You need to stand up and stretch. Are we good? All right, so conventional tomography, again, please pay attention to the words because you may say computed tomography and I'm going to say conventional tomography. We just saw a radiograph of a conventional tomography. It is not an axial image, right? So want to make sure that we're understanding and overcoming our limitations. So we had to do image blurring. We degraded our image contrast. If you looked at that image, it didn't have a lot of great contrast on there. Other problems resulting from film screen back in the day before we were in digital or computer radiography. We had film screen. This is probably why it's not done today, if the CT can do it all. And failure to demonstrate small differences in tissue contrast again. And if we take a look at that image, which I'll probably put on here so that we're able to see it. You can see right there that that is not going, you don't necessarily see any tissue differentiation. What is the white in there? Contrast. And that's because we're able to see at different, as Marquita and Lexus were talking about earlier, different timing sequences. All right. Limitations on conventional tomography. We good? Thumbs up. Let me see them. Okay. Now we are entering back into CT, and you're thinking, why are we starting from the beginning? Because we had an overview in chapter 1. We had an overview in chapter 2. Now we're going to get into more specifics and the physics of what is CT. So again, the benefits of CT over computed tomography, conventional tomography and radiography is going to be minimal superimposition. It's going to be improved image contrast. Improved image contrast. And the recording of very small differences in tissue contrast, which increases contrast resolution. That's what that's called. When you improve the very small differences, and your very small differences in tissues, you have a good resolution. And so it improves tissue resolution or improves contrast resolution of similar type tissues. All right, so now we know who introduced CT into the medical industry. All right, good, and when we're thinking about a brain, because that was the first organ that was radiographed through CT methods, we talked about the CT number 1, generation number 1. James, tell me what's the difference between generation number 1 and generation number 2?
Generation 1 was the
Pencil beam. It was a pencil beam, very limited, very small, which is why it took several hours to complete a whole scan. Perfect. What's the difference between number 2? Who's got number 2? Go ahead.
He has several pencil beams and 2 detectors.
2 detectors. Good. What happened with number 3? Sindhu.
There's the fan beam,
There was a fan beam and
multiple detectors.
detectors that traveled how?
In spiral.
Around. So the detectors moved around the gantry. What about 4? Samantha.
It's where it had the stationary ring of detectors.
I like it. All right, then we also talked about the electron gun. Well, a little bit, right? An electron beam gun uses, or electron beam CT machine uses an electron gun. That's going to come down later. All right. The physical principles, we talked about data acquisition, data processing, image display, storage. You're like, done. I know these like the back of my hand. I can tell you exactly what happens in each and every one of them. That would be a great idea for like an essay, if you really want to read, Miss Laura. Yeah? Romer's nodding his head yes. He's probably going to have a talking to afterwards, Romer. Not joking. But we do know. We know what happens in data acquisition, and the difference between Thaddeus and in your reading, because everybody's read their 4 chapters of the PDFs that was sent to them. Yeah? Okay, so you stopped at 3, good. All right, so in Thaddeus, it really talks about DAS as being DAS. It doesn't really go into anything else specific. It doesn't talk about the ADC. It doesn't talk about electrical signals. It doesn't talk about much of that. It's very high level, meaning it's just talks about the DAS. What does DAS stand for? Data acquisition system. But we know a little bit more because this PowerPoint covers a lot more in detail, which is important to know. So when we think about the data acquisition portion, where do we start our data collection? And I'm saying the word collection. At the detectors, that is the device, right? We do need an X-ray beam. Betsy, walk me through, how do we get an X-ray beam?
Extra beam.
You can phone a friend, we're all family in here. You need 3 things:
Source of electrons.
source of electrons,
Accelerating.
accelerate them, abruptly stop them. Yeah, good, perfect. That's how we get our X-ray beam, because once the kinetic energy is abruptly halted, what are the 2 forms of energy that emerge from kinetic? What is the conversion? Photons being one, and heat is the other one, it's the dominant one. All right, so when we think about data acquisition, we refer to the systematic collection of information from the patient to produce the CT image. Now, there's two methods. We have the slice-by-slice data acquisition. Why did I highlight the volume data acquisition? In which generation are we capable of getting volume? 1, 2, 3, or 4?
3.
Why? Because when the rotation starts to spin, we're going to start talking about pitch eventually, where the table is now moving in sequence as the rotation is happening in the gantry. And this is allowing that helical or spiral scanning to happen. And what we're seeing as it is spinning around and around, as it's spinning around and around, it's a little bit overlapping, so we're going to go back and talk about stitching these areas over one another so you're able to go faster. This is why, how long does a typical scan last for CT? Seconds. Takes longer to get the person prepped than anything. Scanning is done, not MRI. They're not talking seconds. They're talking lots of minutes. And you would think this, the bigger the anatomy, the longer it is, but it's actually not that. All right. So everybody understand that we are talking about volume data acquisition, and we started seeing that in our 3rd generation when it started to go into spiral scanning. Yes? Perfect. Now, what is a slice by slice? The X-ray tube rotates around the patient and collects data for the first slice. The tube stops and the patient moves into position for the next one. So instead of having, kind of like what we saw in that last image, instead of having the spiral scan, we are now taking slice by slice. Okay? Meaning the gantry's here, the patient is moving intermittently. And here, the table or the patient is moving in a nice flow fashion. Right? So there is a stop, move, and this is a continuous move of the table. This is going to make more sense because we're going to start talking about pitch. Everybody understand the difference between slice by slice? Yes? See? We're already halfway through. A single slice CT and a multi-slice CT. What's the difference between those two? The detectors, how, Lexus? Could be the number of detectors, but are they detectors going this way or are they detectors going this way? So So if we have a single row of detectors, right? It's gonna take us longer to catch all of the volume of the abdomen. But if we have multi rows of detector, that's less scanning time because I have less revolutions, right? But I have greater patient dose. Yes? All right, so the volume data acquisition, so we talked about, again, it's all about what are you capturing, and it's all about the detectors. Again, what if it's a single row versus a multiple row of detectors is referred to the spiral of the helical, and this is where you get that term volume tissue scanning, volume tissue scanning, meaning you're doing lots of volume, and again, we're going to overlap, and so we're able to get more information because we have greater rows of detectors, and we're going to be able to put all of those different data to work as the detectors, all of the detectors are converting that into an electrical signal, and our ADC is working in hyperdrive to get that to a digital talk, and then it continues to move forward in the computer and microprocessing. But are we good? What's the difference between slice by slice and volume data acquisition? It's all about the words, guys. Pay attention to the words because you can see the word image or you can see the word volume. Don't automatically assume what it's talking through. So would you be able to identify which one is slice by slice and which one is volume? A is an example of what kind of data acquisition? Slice by slice. We can see the difference in B. We're covering that over. It's going in a spiral. And what is that called? What? Volume data acquisition. Good. Perfect. All right. Do we need to take a break? Where are we? Yeah, let's take 10 minutes. Wakey. We got more to go. We started talking about finals already. Like, now that's the game. You heard, who was talking about attenuation earlier? I think it was in sonography. Maybe I saw that. It wasn't. It's the same. It's the same all around. All imaging. What does attenuation mean? I just wrote it on the board. Loss of protons. Protons, okay. Or either through absorption or scatter. So in order to have attenuation, again, when you are going into the patient and you're seeing these x-rays from the x-ray tube, here's the primary beam, meaning this is high energy beam. They're coming straight out of the x-ray tube, and here is the patient. Depending on what these x-ray photons are going through, you have now what is called the exit beam or remnant beam. This is what's landing on the detectors all the way through, right? And depending on the energy levels, that's going to be deposited. So attenuation is basically happening right here inside of the patient, and it is going to be attenuation. I don't know if I spelled that correctly, but it's been a long day. It's going to be the loss of photons. That's going to be through absorption. When you have a total loss, right? They've been absorbed or they have been scattered. Those are the only two ways that you can have attenuation. Now for the primary beam that is interacting with air and it's not losing anything, what do we call that energy? It's not attenuated, it's what? What's the opposite of attenuated? I'm gonna sleep with a smile on my face. Transmitted. So you have either transmitted photons landing on the detectors, or you're going to have attenuated photons possibly landing on the detector. If they're not landing on the detector, then they were what? Absorbed, lost. They won't be making it to the detector, correct? Make sense? Where would they have been absorbed at? What would be a good absorber of X-rays? Bone. Perfect, because of its high density, right? They're very close together. So the reduction of the intensity means what again?
The amount of photon section.
The amount of photons in the X-ray beam. What technical factors control the intensity or the amount?
The
MA and?
and time.
And time, mass, perfect. So the reduction of the intensity of the beam of radiation as it passes through an object. It's either going to be reduced in intensity through absorption or scattered, meaning we aimed at the detector, but it got scattered and it never landed on the detector. Or perhaps it did in a different area of the detector. So the CT beam attenuation is dependent on woo-wee, atomic density, guys. What does that mean? Density, 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 density. I know you're not trying to remember density. Tissue density. Something that is very compact. So when you think of atomic, you're talking about atoms that has a high dense. So the higher the number of the atom, the likely it's going to be very, very dense. The atomic number of the absorber and the amount of photon energy. Did we have a high mass? Did we have a high KVP? If we had neither of those, chances are those photons are going to be highly absorbed very quickly, depending on the material that we are aiming. So, did everybody understand what I just said? I'm seeing some nods. I'm seeing some glossing over of eyes. I'm also seeing what you're thinking about what you're going to eat when you get out of here. I see all of that. You're thinking about traffic, whatever it is that you're thinking about. So if I give you a pop quiz and say, what are the CT beam attenuation is on 3 things. Here we go with the number 3 again. So I know I like throwing those 3s out there. Did something to my rotator cuff.
Oh, no.
Atomic number is what? Remember what tungsten is. What's the atomic number for tungsten? Google it. You got a computer in front of you. Let's start making you work. Google it. You know it? Yes.
An barium.
That's the atomic number. Atomic number. What is the number represent? 74.
That represents the number of protons surrounded inside the atom. Nucleus.
That not the number? The number represents how many electrons are in the atom, correct? Yes? That's what the atomic number in the periodic table is assigned, so that when we go from hydrogen, which it has a number 1, means it has 1 electron. So 1 proton for balance and then 1 neutron. And we have some isotopes that are probably a bit unstable, but we're talking about this, right? And why tungsten? Why did I pick that one? Keep that number in your mind on what it's called. Hold on to it. Why?
This is high capacity for heat.
It has a high what?
Heat capacity.
Heat capacity. This is why we use tungsten. Where do we find tungsten?
In the coil.
We find it in the cathode, in the filament, which we need to do what?
Boil off electrons.
Beautiful. And where else do we see tungsten?
On
On the
top of
anode.
that.
We see it on the anode disk. Perfect, because it also has a high heat capacity, right? So we can reduce any type of pitting or anything like that from that force. So we know what an atomic number is. Perfect. What is a photon energy? I just give it some more all that. Which one has a higher energy? A. Why? It has a higher frequency, more waves per distance or per time, which is the unit of measure, right? So if we have a photon energy, now we're talking about radiation attenuation. Does a photon that has a high energy or a low energy have the likely ability to get absorbed or scattered? I'll ask that question again. If the energy of the photon, which one is likely going to make it to the detector? A? Why? Because it's high frequency, but why is it likely to make it to the detector? It likely will just not get absorbed, right? It's not likely to be stopped. So the higher the energy or the higher the frequency, the higher the energy of the photon is more likely to exit the patient because it's packing enough punch to get to the detector. A Ferrari, I don't know, and a Volkswagen. I don't know my cars all that much, but I'm gonna say one has a higher speed, right? So chances are the ones that are having a higher speed are likely to get through whatever more than something that is not. Okay? So now we understand what's the difference between photon energy. So high photon energy, not likely to create attenuation, might be transmitted, right? Low photon energy is likely to have some attenuation, whether through absorption or scatter. What about effective atomic density? Atoms per volume. What does that mean? Anybody want to guess on that?
Does it mean how compacted some tissue is?
And the type of atoms that it takes. So if you go back and you look at calcium on your periodic table. Alright, 20. And we know that with enough of the calcium tied closer together, or highly dense tissue, not likely you're going to be able to penetrate through it because there's not a lot of space in between it. Now, if you compare that calcium to hydrogen, which is water, which is what, we're about 60 to 75% water, chances are the photons are going to go through that very easily. So do you think that would be a factor of what is attenuated? The loss or the scatter of photons or the reduction of photons in the beam? Right? So do we all understand what those three mean now? Yes? Perfect. So if I came next Wednesday and said, ooh, the CT beam attenuation is dependent on 3, give it to me. I'm going to hear, let's fast forward, the atomic density, loud and proud. The atomic number. And the, what does that mean? What does photon energy mean again? The energy of it, right? What controls the energy of our beam, our photon? What technical factors? KVP. Remember we learned what energy is, so photon energy there is controlled by KVP. Good. What is the atomic number? It's on the periodic table, right? We're talking about the number of electrons that an atom is going to have, right? And then what is the atomic density? How compact it is. When we think about calcium, we say, oh, that's 20 electrons. If they're all compacted together, then chances are of that photon going through, not likely, right? It's going to be absorbed. Photon is not likely to transmit. It is likely going to be captured or lost, absorbed. All right, perfect. Ooh, homogeneous beam. We're just learning terminology and terminology. So these are some concepts here. When we think about a homogeneous beam, we've heard this concept before. We think about a homogeneous organ. Can someone tell me what a homogeneous organ is? The liver. Why is it a homogeneous organ? Because the liver has one tissue type. It is made of the same tissue. So it is very homogeneous. The kidneys are not. The kidneys has space, right? And the pylorus and different parts of it. So there has some tissue differences in there. But when we think about a homogeneous being, we're saying the same. It is the same. Also referred to monochromatic or mono energetic beam, meaning the energy of the beam is the same. The energy of the beam is the same, monoenergetic. Now, basically what is it saying here? We're still talking attenuation. So if we have 1,000 photons and we go through this substance right here, we're going to lose about 20% of our photons. So now we're out at 800 photons, meaning that this beam is monoenergetic. It's not going to change. All of the photons in that beam are the same energy. That's what monoenergetic means, meaning if all of the photons are 70 keV, electron volts, then every photon in that beam is 70 keV, electron volts, right? Which would be pretty easy to determine what's going to stop it and what's not going to stop it, because we already know. Now we're going to talk about the quality of the beam. We heard that term before. What is the quality of the beam? How hard is the beam? What does that mean? I get it. Y'all made me proud the first half. It runs out after a while. I get it. I get it.
The quality of the beam is said by the KVP means the ability to penetrate.
Score. Yes. So how hard is the beam? How well will it penetrate through what we're aiming? Do we need it to penetrate through what we are aiming? So the quality of the beam energy, does not change as it's attenuated, meaning we started out with 70 keV, we had 1,000 photons, 70 keV, 70 keV, 70 keV, 70 keV, but as it traveled through all of those 5 substances, it reduced the amount of photons that ended, right? Primary beam, exit beam. Good. So this is just basically saying they're using 88 keV, kilo electron volts. That is how a photon is measured. We set our KVP, kilovoltage peak, on our system because we're saying once we set that, no energy of the photon will exceed 88 keV or K, 88 kVp, right? So once you set it, it won't exceed it. But what monochromatic or monoenergetic beam is saying that if I set it at 88, all of my photons are going to be 88. That's what that's saying. They have the same energy. all the way through. That's not what we have. We have a polyenergetic beam. Our polyenergetic beam or polychromatic beam is going to say, oh, well, we're starting off with 1,000 photons, which is controlled by our mass, but we have 88, we have an average, the word mean means average of 40 keV. So as our photons continue to move through these substances, and we're going to call them filters, what happens? Why does the number increase as opposed to decrease like we did in the monochromatic? If we started out with 88 kVp and all of these photons are 88 kVp, and we see that we're reducing exactly 20% at each filter, we're going to call these filters, we start to see a reduction in number. But here, in a polychromatic or polyenergetic beam, the number gets higher. Why?
What number gets higher, Ms. Lauren?
40 keV mean, that's the average of all these photons. We went from 40 to 47, 52 keV, 55, 57 average.
Because the energy that makes it to the end would be the ones with the highest energy.
Because you're hardening the beam. Why?
Turn off the lower-
You're weeding out the weak. How?
Like filters?
Because those photons aren't the same. They are now moving through each filter. They're not high energy anymore, they're low energy, and they're being reduced, making the quality of the beam or the hardness of the beam higher.
And those low energies are not useful, right? They just increase efficient levels.
There you go. And lower our contrast. That's when we're going to get into the bow tie filter. These are filters. So filters will eventually harden our beam, increase the quality of the beam. An X-ray, we do not create, it's not a homogeneous beam. It's not a homogeneous beam. Once we set our KVP, we'll have a mean range, but it is, which is going to be likely 30% lower, what the average setting of the KVP is. So does everybody understand attenuation is not an exponential, rather than both the quantity and the quality of the photons, meaning how many photons you put in there makes a difference, and how is their energy level. If it's a low energy, they're not getting through the filters. It's got to have enough high energy to get through the filter. Got it? Perfect. So the quality of the beam is going to be in sync with its penetration power, which we call it is hardening the beam. How do we harden the beam? Filtration. Good old filtration. Whew, we got through that. We got some concepts down. So what did we go over today? Let's see. Let's look. Everything that we've gone over. You're like, it's enough. We said it below. We know the differences between imaging and radiography. What's the limitation of radiography versus computed tomography? Contrast resolution. Good.
Superimposition. Superimposition.
And superimposition. Are you seeing this on your handout, by the way? I'm like Houdini. Now, what's the limitations of computed tomography?
Conventional computer tomography?
Conventional, you're right. Conventional computed tomography. You're right. Thank you, Romer, for catching me. Romer is on fire today. Conventional tomography. It wasn't computerized yet.
If you get a clear picture, what you focus on, everything else is clear.
Perfect. Marquia's on fire. I like it. We are learning. Now, how does computer tomography improve image contrast? Well, we know that that's a benefit, right? We know that computer tomography eliminates superimposition of anatomical or organs, and then we have an improved image contrast. We haven't quite got there yet, have we? How it does it yet. We just talked about long scale and short scale. Short scale is synonymous with low contrast or high contrast? High contrast. The long scale is more synonymous with low contrast. There's a low difference between each and every one of those titles that we wrote on there. It has a very good contrast resolution, which we're going to talk about next class. We talked about the detector. Is that the first steps of our DAS system? What does DAS stand for, Samantha?
Data acquisition system.
Perfect. So this is where the detectors that starts to collect that data. We talked about data acquisition. We talked about slice by slice data acquisition. Help me, Angelica. What's the difference between slice by slice and volume data acquisition? They're both data acquisition types.
Volume is more.
Volume means more how.
It's superimposed more.
Okay, good. I like it. Look where you're going there. Which one is spiral? Volume or slice by slice? Volume? Good. What does slice by slice do for the table? What kind of table movement is happening in slice by slice? Yes, Lexus? Stop, go. Right? Until the revolution is completed, then it moves to the position of the next one. Right? What's the table movement, Romer, in helical or helical scanning?
It's a continuous movement and it's synchronized with the X-ray and the detectors.
All of these blank stares are turning into a positivity towards the end, guys. I'm sorry, you made it through. If you guys can see what I see, I'm like,
That's my absorption phase.
What? It's absorbing. I'll take it. It's attenuation's happening. All right, so the X-ray tube rotates around the patient and collects data. Okay, what's the difference between a single slice, Sindhu, and a multi-slice CT?
So, single slice. No. Multi-slice have more volume.
How?
Yes. Superimposed.
Okay, I like how y'all are talking back there. I like it. Like volume, superimpose. That means something. I like it. You're on the right track. It's faster. It's just faster this way. But multi-slicing. Which one is multi-slice? This one or this one? What's the difference between the two?
Yeah.
Larger volume because more is being exposed at the same time. So when we say volume, there's more percentage of the body that is being exposed. More data is being collected over these areas. Here, data is only collecting right here. Does that make sense? So this is a lower percentage of body data. It's gonna have to spin more than this one, right? So you would have to increase the spins. This one's going to decrease as many revolutions over because more is required. Make sense? So, which one of these has a greater scan time? Lexus? This one? Why?
has to be more, revolution.
because we would have to increase the revolutions, which is our unit of standard is time, seconds. This one is going to be less time because we are limiting the amount of revolutions. Because we don't need it unless we're trying to scan from our head to our toes. You don't need all that, right? I hope nobody's doing all those scans head to toe. Alright, so we do know the difference between a single slice and a multi-slice CT machine. Perfect. Alright. Ooh. Here we go. Physics. Hello. The reduction of the intensity meaning what again? What does intensity mean?
The amount of photons.
The amount of photons or the quantity of photons in that beam of radiation as it passes through an object, the patient. So if we're reducing the amount of photons, we need three things to reduce them, or likely the three things. One is, how high is that energy, right? So that energy has to be pretty low. It's gonna get absorbed, right? Good. A little Volkswagen. Atomic number, what does that mean? The higher the number, the likely it's going to absorb. Too many electrons in that field to collide with our X-ray beam. And the effective atomic density. We're talking about tissue. Types of tissues that has a higher calcium versus hydrogen. Those are great examples. Air. Air is very far apart, right? Hydrogen is closer together. Molecules have to form. And then in bone, those molecules are compacted. Close to each other. So when you think about it in that perspective, photons are more likely to transmit when the photon energy is I just switched it up on you. I'll ask that question again. What is the level, the photon energy must be what? To increase its chances of transmission, or
Must be high.
must be higher. Good. The atomic number must be lower or higher to attenuate the beam. Is it? Attenuate the beam. What does attenuate mean? Loss. It's reduction, right? Through either loss, absorption, or scatter. So the atomic number must be higher or lower in order to attenuate.
Higher.
Thank you. Thank you, thank you. Those are some great questions, I know it. You see how I'm tricking you going back and forth? Yes, I'm changing what I'm asking. And then the effective atomic density, right? The more compact that tissue is, the less likely it is going to be, and that's why we would have to raise it if we want to transmit. We talked about a monochromatic energy beam, meaning what? What does a monochromatic beam mean? All of the photons in that beam must be same energy, perfect. Polychromatic beam or polyenergetic beam means what? All the photons in that beam are
Different.
different. Good. Now, how do you harden a beam? Alright, so when we get back next week, don't be surprised for a pop quiz. It was not a pop now, is it? Get a quiz to make sure that you keep up with everything. Don't lose it. Hold it in.